This lecture is going to take you through chapter 24, which is about the immune system. The first thing to do in this chapter is define what a pathogen is, and a pathogen is something that causes disease in an otherwise healthy individual. It's important that you understand that there's different kinds of pathogens. Usually people automatically jump to bacteria, but all the other things that I have listed here are pathogens as well. Right now, of course, there's COVID-19 going around. That's a virus. It's a coronavirus. Helminths are worms. People can get tapeworms, they can get pinworms, they can get trichinella. There's a bunch of different worms that can cause disease in human beings. There's fungi. There's yeast that causes things like thrush, yeast infections, athlete's foot. There's mycoses that can be superficial skin infections like ringworm. Protists are things like malaria, amoebic dysentery. Let's see, what are some other ones? Giardia. Those are protists that can cause infections. And then prions are proteins that cause infection. They are indicated in diseases such as mad cow disease, scrapie, which infects sheep, chronic wasting disease, which infects deer. So there's a bunch of different types of pathogens. The reason why it's important that you understand that is each pathogen has to be treated differently, not just by your immune system, but by any medical treatments that we decide to give to a person. You don't treat a bacterial infection the same way that you treat a worm infection, and so you have to use the proper meds to treat either of those depending on which one a person happens to have. Now, the immune system in human beings is designed to counteract any pathogen so that we can clear the pathogen out of the system and then restore health back to the person. There's a bunch of cells and chemicals that are going to help us out with that. Technically, the immune system isn't an organ system because there aren't organs involved in the immune system, or really it's sharing organs with the lymph system. So we've got like lymph nodes and tonsils. Those are going to help the immune system out, but it doesn't have its own dedicated organs, if that makes any sense. I gave you this little table to help compare and contrast innate immunity with acquired. Innate immunity is also called nonspecific. It's called that because it doesn't care what kind of pathogen has gotten in the body. It treats all of them exactly the same. Acquired immunity is also called specific, and it does care. It's the one that's going to be treating a bacterial infection differently from a viral infection, which will be different than a helminth infection. The other reason why they have these names is innate, you're born with it. It works from the moment that you're born, although some of the aspects of it are a little bit slower at first. Acquired, though, you have to learn how to use that, and it doesn't work super well for the first few months of life because you don't have any of that immunity built up just yet. You have to meet a pathogen in order for your specific or acquired immune system to be able to work. So for the innate system, surface barriers try to keep all pathogens out regardless of what type it is. If something does breach a surface barrier, where you're going to use inflammation and phagocytosis to try to control that pathogen. Your acquired immune system, instead of relying on organs and sort of just a generalized inflammatory response, are going to use B cells that make antibodies and T cells that are directed assassins to try to take care of the pathogen and or your cells that are causing problems. And then just other miscellaneous stuff that have to do this. Like I said, this one's always working from the moment that you're born. It does help to keep pathogens out, so it's making this side not have to work as hard, because this side requires a lot of energy from you in order to make it work. The acquired immune system also takes time to meet pathogens, build up your army of defenses. In the meantime, you do tend to develop symptoms as the pathogen is starting to harm you. However, it can completely clear an infection as long as you have the genes to help you make different antibodies and cells that are going to be responsible for clearing that pathogen. I gave you this picture to try to summarize kind of everything that we just said. It's just a different way to look at what we're doing. So innate is also called nonspecific. Adaptive is also called specific. So surface barriers, again, are going to keep things out. Internal defenses include inflammation, phagocytosis. Fever is sort of a systemic inflammation. These two things, they are designed to help you clear the pathogen, but they don't kill the pathogen on their own. It helps to stimulate other things that will kill the pathogen. If you got hot enough to kill a pathogen, you would die too. And so a lot of people have this misconception that fever helps kill bacteria. And really, all it does is help prime your immune system to work better so you can kill bacteria. The fever by itself does not kill them. Adaptive defenses has two branches depending on which type of T or B lymphocyte is going to be responsible for that. So humoral immunity uses B cells that are going to secrete antibodies. And cellular or cell-mediated immunity is going to use T cells, which are direct assassins that murder cells that are doing bad things, essentially. So I mentioned the word phagocytosis earlier. This is the process of cell eating. We talked about it back in the first half of the course white blood cells like this one right here, they just engulf the pathogen and then bring it into the cell and then digest it inside of there. So that's one way to deal with anything. This process is non-specific. It doesn't care if this is E. coli or salmonella. It's going to treat the bacteria the same way, eat it and digest it. A neutrophil is one example of a white blood cell that is capable of phagocytosis. This is what they look like. They have really funky shaped nuclei inside of them that has multiple lobes with constrictions in them. This is the most numerous white blood cell that you have. One of their problems though is they're kind of small cells, and so they eat themselves to death in the process of trying to deal with any pathogens. Macrophages are a little bit better at this though. They're larger cells, they can eat more, and they don't tend to eat themselves to death. They don't tend to be the first at the site of infection though. Instead, if the infection's been a little bit prolonged, the macrophage will get there later. So that just shows you how they chase down bacteria. So that's a couple of little bacterial cells that it's trying to catch. These cells aren't just flowing with your blood, they're actively looking for pathogens to eat, and then they do phagocytosis to eat it. Next up, your inflammatory response is going to help keep certain infections in one place instead of allowing it to spread to other areas. Inflammation tends to be really annoying, really painful, sometimes really itchy when it happens, but it is your body trying to heal an area so that you don't end up with a more prolonged infection. So it's trying to help you out in its own way. Now, inflammation, you can recognize it because of those 4 cardinal signs that we had on the previous page: redness, heat, swelling, and pain. You can see the redness because it's red because we created something called hyperemia. We have increased blood flow to this area, and because there's more blood flow, your blood is warmer, and so that's going to bring the heat that goes along with this. You can see some hives are developing back here. That's the swelling. And while you can't see it in the picture, it's either going to be really itchy or it's going to hurt for this person. And so you can see the signs that go along for that. Now this over here was some type of spider bite, and you can see the inflammation that's going around that. And again, what it's trying to do is prevent what had been in that spider venom from spreading into other areas of the body. Now sometimes it can do a really good job of that. Sometimes whatever was in the venom or bacteria, if it managed to get in there, sometimes it starts to spread. If you ever notice inflammation, the area is getting larger, it's time for you to go see a doctor because it's not keeping it contained like it was supposed to. Now, histamine is the chemical that's released by your immune system to promote inflammation. What it does is it brings more blood to an area, it increases the size of the blood vessels, and it makes the blood vessels, a little bit leakier, so some of the cells and antibodies can start to leak out of the blood vessels in that area. If you have an inflammatory response that is being annoying, let's say due to allergies, you take antihistamines to counteract what histamine is doing to you. What are the 2 main functions of the lymphatic system? So the reason why we're coming back to this very briefly is because, again, your immune system doesn't have its own organs. It shares organs with the lymph system. So I kind of wanted to just tell you what the lymph system's job is. As the blood is moving through the circulatory system, some of the plasma leaks out of the capillary beds in the tissues. And some of it does go back into the capillaries and then the venules, but some of it stays behind and it becomes interstitial fluid. You make a lot of interstitial fluid every day, and you have to get that fluid back to circulation or your blood pressure would drop and you would die. So what happens is we have all these little lymph capillaries. They pick up that excess fluid, and then as the fluid moves back towards the circulatory system, we filter it in lymph nodes so that we can get any pathogens out of that fluid prior to us pumping it back into the circulatory system. So it returns leaked fluid and filters that fluid before we take it back to circulation. This shows you what your lymph system's supposed to do. So this leg, the lymph system's working exactly like it's supposed to. This one, it's not. Now the reason it's not is the person has this worm that has gotten stuck in one of the lymph nodes, and so basically it's created a cork that is preventing the fluid from going back up towards the circulatory system. So your lymph system prevents this from happening all day, every day, and I think we can all say thank you, lymph system, even though nobody usually knows that it even exists in the body. So lymph is the fluid that is being returned back to circulation. It's essentially the same thing as blood plasma. It's just that it's in a lymph system vessel now, and so the name has changed. Oh, it was also on that one. So lymph node filters. Now, I don't know how much you guys remember about your history lessons, but back in the 1300s, there was a plague. That plague had various names: Black Death, bubonic plague. A bubo is a swollen lymph node that results due to infection, and in this case you can see lymph nodes that are in what's known as the inguinal region that are becoming very inflamed, and so the lymph nodes are inflamed due to infection in this person, and so those are bubos, or what your doctor calls swollen glands, but they're really swollen lymph nodes. So this is exactly what I was just talking about just a second ago. So you have 3 clusters of lymph nodes in your body where there's just a bunch of it in one place. The cervical region is one, and that's what this is trying to show you. So this is a swollen gland, what your doctor would call, but really it's a swollen lymph node. These lymph nodes are perfectly fine. You also have clusters of lymph nodes in your axillary regions, which are under your arms and your armpits, and then that inguinal region that I showed you in the previous picture. An antigen is a substance that can provoke an immune response. Pathogens are antigens, but there are also antigens that are not pathogens. So antigens can be things that your body dislikes, but those things might not have been trying to hurt you. Like there are people out there who are allergic to cat dander. Well, that's an antigen, but it's not like the cat dander was trying to murder you. It's just your immune system is unhappy with it. And so that's an antigen that's not a pathogen. One of the tools that you have to try to deal with those antigens is antibodies. I want you to kind of consider antibodies like they're bullets that can be fired by your immune system. In reality, they're proteins, and what they can do is they can bind to specific antigens, and again, it is specific. This is part of your specific defense system or your adaptive immune response. So this antibody or bullet couldn't attach to this antigenic determinant on this side or this antigen shape. It couldn't attach to this one, but it can attach to this one. Only if it can attach based on the shape of the molecule can we actually do the bullet thing and try to murder that antigen. A vaccine is something that we give a person to try to provide that antibody response without them actually getting sick. And usually the way that we do that is we weaken or kill the virus, the bacteria, whatever the pathogen happens to be. And then we inject that weakened or killed form into a person. There are newer vaccines that are being developed based on RNA technology and a whole bunch of other different things as well. But what they are doing is introducing you to an antigen that is so weak it can't hurt you, but it can still prime your immune system so that your immune system recognizes that pathogen in the future, and so you don't develop any symptoms at any point during a vaccine-derived immune response. So one of the things that is happening in America is people have decided that they are smarter than doctors and smarter than epidemiologists, and so they have decided that vaccines are not good for you. And that is, it's a double-edged sword sort of a thing. There can be negative health effects to vaccines. In fact, right now there is an outbreak of polio in Africa that was vaccine derived because they had used a weakened form of the polio virus. Well, it regained virulence, and so there is an outbreak that is derived from that vaccine. So I am not saying that they never have side effects or repercussions, but what I am saying is they don't do what those anti-vaxxers say they do. They don't cause autism. They very, very rarely have any of those really detrimental side effects. If you've ever seen a child that has to go through tetanus, you would way rather vaccinate them to tetanus than have them go through that disease. And what it does is it makes the muscles contract so hard it will literally break the bones in the body. And tetanus does not really get a whole bunch of side effects that go with it. The vaccine, doesn't. So please vaccinate. If you have not had your Tdap or DTaP or MMR vaccines in the last 10 years, you're supposed to get those every 10 years to make sure that you still have a nice antibody titer against those things. Just basically the moral of the story here is please vaccinate your kids. They do work. They are safe. The vaccine that we had been sending to Africa for polio, we don't even use that same vaccine in the U.S. We use a killed virus for it, and so it's a very safe vaccine in the United States for United States citizens. This is another one of those things everybody goes back to. Well, back in the old days, we would have chicken pox parties. So my kid would get chicken pox. We'd invite their whole class over so they could all get chicken pox at the same time. What I want to point out is people do die of chicken pox every year. The other thing that people don't seem to understand is the virus that causes chicken pox, once you clear the infection, it's actually not gone. It's hiding in your nervous system, and it can come back later as what is known as shingles. And shingles, the best way that I've ever heard it described is to imagine that you have a part of your body that is on fire 24/7 and there's nothing that you can do to put that fire out, that's what shingles feels like. And I think if you've ever met a person who has shingles, you will know, yes, it does hurt them. Not to mention when they have an active shingles infection, they are highly contagious. And so if they get introduced to a baby that hasn't been vaccinated, they can give that baby chickenpox, and that can lead to a fairly severe infection. It's this misconception of everybody thinks it's just this, oh, you get itchy, but you get better. And it's very important that you know, like the flu, chickenpox does kill people every year. And so the vaccine is a way better option. This is from the CDC. I didn't pull this up recently, so the vaccine schedule does change periodically. But what it shows you is the vaccination schedule for babies. And notice that they are not getting varicella until, which is chickenpox, if you didn't know that, until they're a year old. So that goes back to if a grandparent has shingles and they hold their newborn grandchild, their grandchild can get it, and it can have very severe repercussions for that. You don't get your third and final dose of Hep B until you're about a year old. You don't get your full immunity against MMR until later in life. Your Tdap vaccine also covers pertussis, and you don't really get your full range of pertussis until you're older, and pertussis is something that can be deadly in babies, and so that's another one of those. Your babies aren't fully protected until they've had at least 3 doses of some of these things, and so it's important to try to make sure that you're protecting them against people who they didn't want to get vaccinated, and so they get measles, and then they bring measles around your baby, and your baby's not protected yet. And so one of the things about vaccines is that it creates what's known as herd immunity. Because there are so few people who can get the infection because of vaccines, your baby is safe because that infection is not going to be going through the population. But because of anti-vaxxers, your babies aren't safe anymore because you start to get those infections like measles and mumps and pertussis that come back around because we've lost that herd immunity. This is older kids and adults, and it just shows you when you're supposed to be getting those backup shots and things. Let's see. Next up, active versus passive immunity. Active immunity means you have met a pathogen, you have made your own army, you're firing your own bullets, and you are actually immune to something. Passive, however, means you are borrowing somebody else's army, and the problem with that is this is not permanent. It can save you right now in an infection, but those antibodies are going to go away. Your kidneys are going to excrete them. And so this is a temporary protection that you can borrow from somebody else. Right now, for example, with the COVID-19 thing that's going around, there are people who have recovered from COVID-19 who are donating their plasma. Well, in that plasma, you have their antibodies that they made that helped them get better from COVID. And we're giving those antibodies to somebody else who has a severe infection. That's a type of passive immunity. And it can save their life right now, but it means they could get COVID-19 again in the future because they never actually developed active immunity to something. Let's see. So that helps you get your little table filled out. That's in page 2 of the notes. This is more of the table. You can pause it so you can write that stuff down. I give you some more examples going through there. Now, here's another little story that I want to give you. With dogs, you can vaccinate your dog against rattlesnake bites, and that's because dogs actually have genes that allow them to make antibodies to fight the venoms that are made by the snakes in our area. Human beings do not have those genes, which means you cannot make those antibodies, which means you cannot be immune to snake bites. There are people out there in the world who believe that if they drink snake venom, it will make them immune to snake toxins, and that is not the way it works. In fact, drinking snake venom makes you more sensitive to it so that if you do get bitten, you will die faster than you would have had you not been drinking the snake venom. There are lots of stories in the literature. Fairly recently, there was an evangelical preacher who used to use rattlesnakes in his shows to show that God will heal him. Well, after the 5th time, God apparently got pissed off at him and he died from the snake bite because, again, human beings cannot be immune to snake venom. Now, here's the story that kind of goes along with this. If you do get bitten by a venomous snake like this copperhead in the picture, you can go to the hospital and they will give you antivenom. Now, I mentioned dogs can make antibodies. Well, so can horses. When people go out and they milk a snake, they collect venom from that snake, and then they inject that venom into a horse. The horse makes antibodies. We collect blood from the horse. We collect the antibodies from that blood, and then those antibodies are what antivenom actually is. So this is a type of passive immunity that we give a person who's been bitten by a venomous snake that will protect them from the snake this time, but if this kid gets bitten again, he is not immune to that snake bite. He was just given a borrowed army so that he didn't die this time around, but he is not actually immune to that. All right, continuing on, lymphocytes. This is another one of our types of white blood cells. So neutrophils and macrophages are white blood cells, so are lymphocytes. These are the ones that are going to give you what you consider immunity. So these are the ones that are part of your adaptive immune system that are going to recognize a pathogen and kill it before you ever even develop symptoms of that illness. Lymphocytes come in two types. There's B cells and T cells. They're named based on where they mature. So B cells mature in the bone marrow. These cells are going to be specialized for making antibodies, which again, bullets that we can use to shoot pathogens. T cells mature in the thymus gland. These guys don't make antibodies. Instead, they dump poisons onto pathogens to kill the pathogen. So think of them like they're assassins, where their preferred method of murder happens to be poison instead of bullets. We kind of had this in a previous picture in the notes, but just go ahead and get it again. Humoral immunity uses B cells that make antibodies. Cellular uses T cells that work in solid tissues by releasing poisons. I've already given you all the notes that you need to go along with clonal selection, and there's nothing for you to fill out there, but I'll kind of give you the rundown of the picture. So an antigen, let's say salmonella, comes into your body. It's going to challenge a bunch of different white blood cells. Now, some of your lymphocytes have these receptors on them, and they are all specific for a specific pathogen. So salmonella will challenge this B cell, but this one doesn't have receptors that match the antigen. So this one does not accept the challenge. This one does not accept the challenge, but this one has receptors that fit the shape of the antigen. So it accepts what's known as the antigen challenge. And at that point, it decides to go down a path called clonal selection. What it does is it divides by mitosis over and over and over again to make an army. It's literally a clone army. And then some of this army is going to differentiate into cells called plasma cells that make a bunch of antibodies. And some of them are going to become memory cells that live for a very long time so that you can remember that infection sometimes 30 years later, so that if you get re-exposed, you don't actually develop any symptoms and your immune system just clears it. So that's how clonal selection works. So plasma cells is that branch of the clone army that fires the antibodies out, and memory cells are the branch of the clone army that just live for a really long time. These are B cells that are plasma cells, and they have a bunch of ER that just churns out antibodies all day, every day. I don't know why that doesn't want to click all of a sudden. I already said memory cells, so we should be good there. So next step. Let's say that you go outside and somebody with COVID-19 coughs on you today. You've never met coronavirus, the new novel coronavirus, before. And so coronavirus starts to wreak havoc in your body, but at some point it does actually antigen challenge some of your immune cells. Since they've never met it before, though, it takes them a while to make their clone army. This is your primary response. So this is you accepting the antigen challenge, contributing to clonal selection, making your clone army, and then your clone army starts firing a whole bunch of bullets, which are the antibodies, and eventually the antibodies get the COVID-19 under control. If you get re-exposed again later on, well, you already know how to make your clone army now. You already had antibodies circulating in your bloodstream, so you get a secondary response. Not only is the secondary response faster, it's also stronger. You make way more antibodies the second time you're introduced to a pathogen than the first time. And again, most of the time you don't even get symptoms the second time, third time, eighth time you get exposed to something, because your secondary immune response is just faster, stronger, better than the primary immune response was. Antibodies, I keep calling them the bullets. They have what most books call a plan of action. I've already given you the notes for what that means. They can precipitate toxins. They can contribute to cell lysis, which is where you pop cells. They can agglutinate cells together so that they're less likely to circulate through the bloodstream. And then they can cover binding sites so that the antigen can't actually bind to any of your cells. So this just kind of shows you in picture form what's happening. So neutralization is cover the binding sites. Agglutination is clump cells. Precipitation is clump toxins. And then cell lysis is pop the cell. Next up, there's different kinds of T cells, just like there were different kinds of B cells. Cytotoxic T cells are assassins that work by poison. Helper T cells are what I usually like to call mom, because if you have a problem in your life and your mom is still around, you go to mom and mom fixes your problem. Mom can do a bunch of different things. So she can stimulate B cells to make their clone army faster. She can stimulate cytotoxic T cells to go assassinate things faster. She can also promote inflammation. She can promote phagocytes to do their job better. She can basically do everything, but she doesn't directly kill things on her own. Instead, she tells everybody else to do her bidding, and that's another reason I call her mom. Self-proteins are exactly what they sound like. They're proteins on the outside of your cell that mark a cell as yours. We don't want your cytotoxic T cells to come murder your cells if they're doing what they're supposed to be doing. And so these self-proteins tell the cell, hey, I'm yours. I'm doing what I'm supposed to be doing. Please don't kill me right now. So I think I told you guys this story last semester, but just in case I didn't, the top picture is Katie Stubblefield. These two are both Katie Stubblefield. She was having a bad time, and she tried to commit suicide by shooting herself in the face. She had a face transplant. This is the person who donated her face. She actually died because of the opioid epidemic. She overdosed on an opioid. And so this face is the same face that you see right here on her. The reason that it looks swollen right now is because the face has her self-proteins on them. They don't have Katie's. That means when her immune system gets up into the face, they don't recognize this tissue. It doesn't belong to Katie. So her immune system is trying to kind of kill the cells that are in here because it's not hers. And that's what's leading to all of that inflammation that goes along with that. So your self-proteins are what they try to match up when they do tissue donation so that your immune system is less likely to reject it. Next up, you have explain the disease caused by the human immunodeficiency virus, which is HIV. So it does cause AIDS, which is the blank that you're filling in for this chunk of notes. These are older pictures at this point, but each little red dot in those pictures marks a person who has HIV in the state of Texas. There's a 10-year gap in between them, and what I want you to notice is the number of people that had them drastically increased between 1997 and 2007, and it continued to increase more recently. I just don't have the map for that because TDH stopped making maps that looks like this. We are right here in Johnson County. If you live in Cleburne, you're right about there. So what I want you to notice is it is here in our county, in our city, there are people living with HIV and AIDS. People seem to think it's not in our town, it's not in our area, I'll be safe, it'll be okay. And essentially what I want to tell you is every one of these red dots thought that at some point, and look at all the people who ended up contracting this disease. So just know that it is here. Now you catch it by having unprotected sex with a person who has it. You cannot get it through kissing, hugging, shaking hands, anything like that, but you can also get it through sharing needles. Anytime you exchange body fluids with another individual, there is a chance that HIV can cross that line. So just protect yourself. If you are a person who uses drugs through needles, never use somebody else's needles. Always sterilize needles if you have to reuse a needle, but honestly, needles weren't meant to be reused. You should be using a clean, sterile needle each time you inject something, whether you're injecting it legally or illegally. Please use a sterilized needle, and then just protect yourself. This is from the World Health Organization, and it shows you the prevalence of HIV when we first started to learn about it in the 1980s versus 2005, and you can see, again, increase in the number of cases. So protect yourself. Autoimmune diseases. This happens when your body stops recognizing your tissues as yours, and so it starts to attack your cells. There's a bunch of different types of autoimmune diseases. She has pemphigus. I'm assuming that's a she just because the waist is kind of narrow, but I don't know. These are some of the other ones. So type 1 diabetes mellitus used to be called childhood onset diabetes or juvenile diabetes. These are the ones that usually have insulin pumps. They have to monitor their blood sugar all the time. This is not like my fat uncle got diabetes. That's a different type. Lupus affects all of the body systems, but it particularly damages the kidneys. Rheumatoid arthritis affects the joints. Multiple sclerosis affects the nervous system. Essentially, there's an autoimmune disease for every possible organ that's out there. I'm not going to go through all of these again, but that's just some of the pictures of some of the different autoimmune diseases that are out there. Next up, allergies. So there is a hypothesis out there that is called the overclean hypothesis. And essentially, the way that the evidence supports it is when you keep a child too clean, you give them antibiotics too early, their immune system doesn't develop right, it gets bored, and it starts to attack stuff that it shouldn't be attacking, like dust mites and pet dander. That's what allergies are. And so if you allow your child to go out and essentially get infections and get better on their own, they would be less likely to develop allergies later on in life. Now, allergens are things that promote that allergic response. What they do is they stimulate mast cells and basophils to degranulate histamine so that you're constantly producing more histamine than you're supposed to. Again, treatment for this is usually going to be an antihistamine like Benadryl or Zyrtec or Claritin. These are all over-the-counter ones, the ones that I mentioned. I do want to specify that Benadryl, it has been shown that if you drive the day after you've taken Benadryl, you are more impaired than if you had been drinking that same day. And so please don't take Benadryl and then drive around the next day. It impairs your mental capacities. And so you also should not be taking Benadryl every single day because it does tend to give you this mental fog. Now, anaphylaxis or anaphylactic shock, this is what can happen if an allergen gets directly into your bloodstream. And so I'm giving you a bee sting as an example there. What it does is it promotes all of your blood vessels to relax all at the same time, and that makes your blood pressure drop. If it drops too much, blood's not getting to all the tissues in your body anymore, and so tissues start to die, most notably the brain. So it can be fatal, often is fatal if not treated. EpiPens have been in the news a lot the last few years because the price has skyrocketed. EpiPen is a specific brand made by a specific company. You can also get epinephrine in bottles that's significantly cheaper. You just have to refill it with new needles, and it doesn't auto-inject like an EpiPen does. But what this does is it causes vasoconstriction. That cancels out the drop in blood pressure so that you can get to a hospital. But if you've used an EpiPen, you're not supposed to just go skipping about through the rest of your day. You're supposed to go to a hospital for further treatment. This is the summary drawing that I wanted you to do. Essentially what it shows you is what happens when an antigen like salmonella first gets into your body. Probably one of the first things that happens is a phagocyte like a macrophage eats it. It comes and it tells mom. Mom then stimulates both humoral immunity and cellular immunity by stimulating B cells to differentiate into plasma cells that make antibodies. P.S. This is spelled wrong. It's antibody, not antibody. Mom also stimulates cytotoxic T cells to dump more poisons and kill cells that aren't supposed to be there or are doing things they're not supposed to be doing. What this picture also shows you is if you get re-exposed to that same antigen, you have an army of memory cells that were hanging around to give you a secondary response that is faster, stronger, better than your primary response was. At this point, I'm going to put a quiz in Schoology for you guys that covers some of the immune system. So look for that quiz.